Something violent is turning toward us from the far side of the sun, not a planet, not an asteroid, not a wandering object coming through the dark. It is part of the sun itself, a region of magnetic violence that was already erupting before it fully came into view. While much of Earth went through ordinary days, while phones charged on bedside tables and satellites crossed silently overhead, observers were watching the solar limb for the first signs of a great active region rotating into our line of sight. From Earth, the sun often feels steady. It rises, it warms the roof, it throws pale rectangles of light across a room, and then it leaves. We treat it like a background condition. A lamp, a clock, a predictable furnace hanging at the center of the day. But that is not what the sun is. The sun is a magnetic machine the size of a star, and sometimes the machine knots itself into places where the stored energy becomes too much to hold. Those places appear to us as sunspots, dark stains on the bright face of the sun. They look like wounds. They are cooler than the material around them, but only by solar standards. They are still hotter than anything human beings can build on Earth. They are dark because the rest of the sun is brighter, and they exist because magnetic fields have punched through the solar surface and begun to suppress the normal rising and falling of hot plasma beneath them. A sunspot is not a hole in the sun, it is not an object sitting on the sun, it is a magnetic disturbance made visible. Beneath it, charged gas is being forced to obey invisible lines of force. Around it, those lines twist, stretch, braid, reconnect, and sometimes break into a new shape. When that happens, the sun can release more energy in minutes than human civilization uses in years. Welcome to Dark Matter Radio. Tonight we are not looking at the sun as a symbol of life or warmth, or the beginning of a morning. We are looking at it as a star that can reach across 93 million miles and touch the electrical nervous system of civilization. The story begins with a sunspot region rotating toward Earth. But the real subject is larger. It is the fragile agreement between a restless star, a magnetic planet, and a technological species that has quietly built its life inside the space between them. The unsettling thing about space weather is that it does not feel like weather. Rain announces itself. Wind moves trees. Thunder shakes the windows. A storm on the sun gives you none of those warnings directly. The sky may be blue. The air may be still. A person may be standing under noon light with no sense at all that photons from a flare have just reached the top of the atmosphere, or that a cloud of magnetized plasma is crossing the inner solar system in our direction. Most of the time that distance protects us. The sun is far away, space is wide, eruptions miss. Magnetic clouds pass above or below Earth's orbit, radiation spreads out. The planet has a magnetic field, an atmosphere, and layers of defense that do not ask for attention. But sometimes the geometry lines up. A flare bursts from a region facing Earth. A coronal mass ejection follows. The solar wind changes. Earth's magnetosphere compresses. Currents begin to flow through the upper atmosphere and through the ground beneath our feet. For most of human history, the result was beauty. A strange light in the northern sky. Curtains of green and red moving over forests, oceans, and frozen ground. People wrote about armies in the heavens, fires over the horizon, spirits, omens, and gods. The aurora was a message with no known sender. Now we know it is charged particles guided by magnetic fields into the upper atmosphere, where oxygen and nitrogen glow. The beauty is real. So is the physics behind it. In the modern world, the same event has another face. A strong solar storm can disturb radio communication. It can degrade navigation. It can interfere with satellites. It can increase radiation exposure for astronauts and high-altitude aviation on polar routes. In the most severe cases, it can drive currents into long conductors on Earth, including power grids and pipelines. The aurora is not just a light show. It is the visible edge of an invisible electrical disturbance. This is why a sunspot rotating into view matters. Not because every large sunspot is a threat. Not because every flare produces catastrophe. Most do not. The sun is active all the time, and Earth is struck by the consequences of solar activity more often than most people notice. But a large, complex active region is a place where the sun has stored magnetic stress. It is a place where the surface is telling us that something below and above it is twisted. To understand why, imagine a pot of water on a stove. Heat rises from below. Hot fluid moves upward, cooler fluid sinks. The surface churns. Now imagine that the water is electrically charged, and that a magnetic field runs through it. Every motion pulls on the field, Every rotation twists it, every rising plume drags it. The sun is not water, but this image helps. It is plasma, a gas so hot that electrons have been stripped from atoms, making the material responsive to magnetic fields in a way ordinary air is not. In plasma, magnetism is not decoration. It is architecture. Magnetic fields can guide motion, store energy, and shape enormous structures. On the sun, magnetic loops rise through the photosphere, the visible surface. Where a loop emerges, one magnetic polarity appears. Where it dives back down, the opposite polarity appears. Many sunspots come in pairs because they are the 2 feet of the same magnetic structure. One foot is like the north end of a magnet. The other is like the south end. Simple sunspot pairs can be relatively calm. Complex sunspot groups are different. They contain multiple magnetic polarities packed close together, sometimes with opposing fields forced into tight contact. That is when the region becomes unstable. The magnetic field is like a field of stretched rubber bands, except each rubber band is invisible, immense, and tied into plasma hotter than a furnace. Stress builds. The sun tries to find a lower energy shape. Sometimes it does that gently. Sometimes it snaps. The snapping is not a literal breaking in the everyday sense. Magnetic field lines are not wires, but in a plasma, magnetic fields can reorganize through a process called magnetic reconnection. Field lines that were connected in one pattern change partners and reconnect in another. Energy stored in the magnetic field is converted into heat, motion, and accelerated particles. This can produce a solar flare, a sudden brightening across the electromagnetic spectrum. A flare is light and radiation. It moves at the speed of light. If a flare erupts from the sun, its electromagnetic signal reaches Earth in about 8 minutes. There is no warning after the fact. By the time we see it, the radiation is here. The most immediate effect is often in Earth's upper atmosphere, where X-rays and extreme ultraviolet radiation increase ionization. That can disrupt high-frequency radio communication on the sunlit side of Earth. The day side gets hit first because that is where the atmosphere is facing the flare. This is why space weather agencies classify solar flares by their X-ray brightness. The letters go A, B, C, M, and X. Each class is 10 times stronger than the one before it. A C-class flare is modest. An M-class flare is stronger and can cause moderate radio blackouts. An X-class flare is the largest category. There is no fixed ceiling above X. An X2 flare is twice as strong as X1. An X10 flare is 10 times stronger than X1. The scale keeps going because the sun does not stop at human categories. The flare itself is only part of the story. Sometimes a flare is accompanied by a coronal mass ejection, usually shortened to CME. A CME is not just radiation. It is matter. It is a vast cloud of magnetized plasma lifted from the solar corona and thrown into space. The scale can be difficult to hold in the mind. A CME may contain billions of tons of material. It may expand until it is wider than planets. It can cross the space between the sun and Earth in a day or two if it is fast, or several days if it is slower. The difference between a flare and a CME matters. A flare is like a flash of light and radiation from an explosion. A CME is like the blast wave and debris, though even that image is imperfect because the cloud is magnetic. A flare can disrupt radio almost immediately. A CME can arrive later and interact with Earth's magnetosphere. Some powerful flares produce no Earth-directed CME. Some CMEs arrive without dramatic flares. The sun does not always package its violence in the way our categories expect. This is the first caution in any story about a sunspot turning toward Earth. A dangerous-looking region is not a promise of danger. It is a possibility machine. It may produce flares that miss. It may launch CMEs in the wrong direction. It may decay. It may rotate across the Earth-facing disk and do very little. Or it may erupt at the wrong moment from the wrong position, with its magnetic field oriented in the wrong way for us. Space weather is a game of timing, direction, and magnetic geometry. The sun rotates, but not like a solid ball. Because it is plasma, different latitudes rotate at different speeds. Near the equator, one rotation takes about 25 days. At higher latitudes, it takes longer. From Earth, because our planet is also moving around the sun, the apparent rotation of solar features is often described as about 27 days. This means an active region can disappear around one limb, cross the far side, and return again weeks later if it lasts long enough. We used to be almost blind to the far side. The sun's visible disk was the disk facing Earth. A region on the far side could be active, but we had to infer its existence indirectly. Now spacecraft give us better hints. Helioseismology can read waves moving through the sun and map some far-side activity. Solar observatories at different positions can sometimes see regions before Earth does. This changes the emotional texture of solar watching. We are no longer surprised only when the storm arrives. We can sometimes see the storm factory before it turns toward us. That is what makes the current kind of news story so compelling. There is something almost ancient in the image. A dark region, not yet fully visible, has already shown its power. It is coming around the edge. It has not aimed at us yet. It may never do anything dangerous. But it is approaching the part of the sun where, if it erupts, Earth becomes part of the calculation. The human mind is built for threats with faces. A predator at the tree line, smoke over a hill, a wave on the horizon. Space weather has no face. The sun is too bright to look at. The dangerous part is hidden in data. X-ray flux curves, magnetograms, coronagraph images, proton counts, KP indices, warnings named with letters and numbers, R for radio blackouts, S for solar radiation storms, G for geomagnetic storms. The danger is translated into scales before ordinary people know it exists. The magnetogram is one of the more revealing ways to look at an active region. Instead of showing the sun as a yellow disk, it maps magnetic polarity. One polarity may appear white, the opposite may appear black. A simple region looks organized, like a pair of magnets. A complex region looks tangled, with black and white pressed together in crowded patches. When strong opposite polarities sit close across a narrow boundary, the region can become flare-productive. It is a map of stress. Sunspots themselves have structure. The darkest core is called the umbra. Around it is the penumbra, a lighter, filamented region where magnetic fields lean outward and plasma flows in complex ways. Through a telescope with a proper solar filter, a large sunspot can look almost organic, a dark eye with hair-like textures around it. But it is not alive. It is physics made visible at a scale where Earth could be swallowed inside a single blemish. The word blemish is misleading. A large sunspot can be many times wider than Earth. The sun is so enormous that even a spot visible to amateur observers through safe solar filters can be a planetary-scale object. When someone says a sunspot is dark, remember the comparison. The umbra is still glowing with heat. It only appears black because it is surrounded by the blinding brightness of the photosphere. A sunspot is a cooler region on a surface that is still thousands of degrees hot. The photosphere is not a solid surface. It is the layer from which most visible sunlight escapes. Beneath it, energy has spent a long time working outward from the sun's core. In the core, hydrogen nuclei fuse into helium, releasing energy. That energy moves through the radiative zone, then the convective zone, and finally reaches the surface in a restless pattern of granules. Each granule is a cell of hot plasma rising, cooling, and sinking. The sun's surface is a boiling pattern of light. Magnetic fields disturb this pattern. Where the field is strong, convection is partly suppressed. Less hot material rises from below. The surface there cools relative to its surroundings. The spot darkens. But the same magnetic structure that makes the spot dark also stores energy in the corona above it. The corona is the sun's outer atmosphere, incredibly thin compared with the surface but heated to millions of degrees. It is a place of loops, arches, streamers, and sudden releases. This is one of the sun's great puzzles. The corona is much hotter than the visible surface below it. You would expect temperature to fall as you move away from the heat source, like stepping away from a fire. But the solar atmosphere does not behave like a campfire. Waves, magnetic fields, reconnection, and turbulent plasma processes move energy upward and heat the corona. The details are still an active area of research. Even the star closest to us remains strange. When a flare erupts, the corona can light up in X-rays. Particles can be accelerated to enormous speeds. Electrons spiral along magnetic field lines and produce radio bursts. Protons and heavier ions can be energized and spread through interplanetary space. This is why astronauts are part of the story. On Earth, the atmosphere and magnetosphere absorb and deflect much of the hazard. In space, especially beyond low Earth orbit, the protection is thinner. A major solar particle event during a mission can become a serious radiation risk. The Moon has no global magnetic shield like Earth's. Mars has only patchy crustal magnetic fields and a thin atmosphere. A crew on the lunar surface, a spacecraft headed to Mars, or astronauts outside a station cannot treat the sun as scenery. They need forecasting. They need storm shelters. They need mission rules. The more human activity expands into space, the more space weather becomes not an academic subject but an operational condition. Satellites live in this condition every day. They orbit inside or near the edges of Earth's protective environment. A geomagnetic storm can heat and expand the upper atmosphere, increasing drag on satellites in low Earth orbit. It can change the density of the air at altitudes where spacecraft normally glide through near vacuum. That drag can alter orbits. It can complicate tracking. It can shorten mission lifetimes. Satellites may also experience charging, electronics upsets, and navigation errors. GPS depends on signals traveling from satellites to receivers on Earth. Those signals pass through the ionosphere, the ionized upper layer of the atmosphere. During space weather disturbances, the ionosphere becomes irregular. Radio signals can slow, bend, scatter, or scintillate. A phone may still show a map. A car may still navigate a road. But high-precision systems, aviation, surveying, agriculture, offshore drilling, financial timing, and military operations depend on timing and positioning accuracy that space weather can disturb. The power grid is vulnerable in another way. During a geomagnetic storm, changes in Earth's magnetic field induce electric fields at the surface. Those electric fields can drive currents through long conductors. Transmission lines are long conductors. Pipelines are long conductors. Under the wrong conditions, geomagnetically induced currents can enter transformers, push them toward saturation, cause heating, distort voltage, and stress equipment. The grid was not built with the sun in mind, but the sun can reach it indirectly. This is where the story stops feeling like astronomy and starts feeling like infrastructure. The sun does not need to destroy anything physically. It only needs to change the electromagnetic environment around Earth enough that systems built for normal conditions operate outside their design expectations. Modern civilization is a network of networks. Electricity, satellites, radio, aviation, navigation, communications, finance, emergency response. Space weather touches the invisible dependencies between them. There is a famous historical warning from 1859. It is called the Carrington event after the British astronomer Richard Carrington, who observed a sudden bright flare on the sun on September 1st of that year. Within about a day, Earth was struck by an extraordinary geomagnetic storm. Auroras appeared at low latitudes. Telegraph systems failed, sparked, shocked operators, and in some reports continued to send messages after batteries were disconnected because currents induced by the storm were flowing through the lines. The telegraph world was small compared with ours, yet even then, solar activity found the wires. That is the unsettling part. The Carrington event did not happen to a technological civilization like ours, but it offered a preview. If a storm of similar scale struck today, it would not meet a few telegraph lines. It would meet satellites, aviation routes, undersea cables with powered repeaters, electrical grids, transformer networks, radio systems, and billions of devices that assume the global electrical environment will remain within familiar boundaries. Nobody should speak about a modern Carrington-level event with lazy certainty. It is not useful to say civilization would simply end. It is also not useful to say there is nothing to worry about. The truth is more technical and more unsettling. Damage would depend on the storm's strength, duration, magnetic orientation, ground conductivity, grid design, transformer vulnerability, operator response, and the state of preparedness. Some systems would ride through. Some would fail locally. Some failures could cascade. The point is not apocalypse. The point is exposure. Space weather forecasters do not watch the sun because they expect disaster every week. They watch because timing matters. A fast CME with a southward magnetic field can couple strongly with Earth's magnetosphere. Earth's magnetic field points generally northward at the dayside boundary. If the incoming CME field has a strong southward component, the fields can reconnect more effectively. Energy flows into the magnetosphere. The system becomes disturbed. Auroras brighten, currents intensify. The storm becomes more geoeffective. That word, geoeffective, is quiet but important. It means the solar eruption actually affects Earth. A spectacular explosion on the Sun may be visually impressive but geo-effectively irrelevant if it is aimed elsewhere. A less dramatic CME can matter more if it is directed toward us and has the right magnetic configuration. For Earth, the most dangerous solar event is not always the most beautiful in a solar telescope. It is the one whose trajectory and magnetic orientation connect with our planet. Forecasting that connection is hard. We can see flares almost immediately. We can watch CMEs leave the Sun with coronagraphs, instruments that block the bright disk so the faint corona becomes visible. A CME may appear as a bright expanding halo around the Sun if it is coming toward or away from Earth. But early images do not always tell us the internal magnetic orientation of the cloud. Spacecraft near the L1 point, about 1 million miles sunward of Earth, can measure the solar wind before it reaches us. That gives warning, but sometimes only tens of minutes to an hour for the most important magnetic details. This is like seeing dark clouds days away, then learning the exact wind at your front door only shortly before impact. We can model, we can estimate, we can improve, but the Sun remains difficult because the thing that matters most is not only the mass and speed of an eruption, it is the magnetic structure carried inside it, and that structure evolves as the CME travels through space. The Sun's activity rises and falls in an approximately 11-year cycle. At solar minimum, there are fewer sunspots and fewer major eruptions. At solar maximum, sunspots become more common, flares and CMEs become more frequent, and the Sun's magnetic field becomes more complex as it approaches a polarity reversal. NASA and NOAA announced that the Sun had reached the maximum period of solar cycle 25 in October 2024. But maximum is not a single moment like the top of a thrown ball. It is a period, and powerful eruptions can occur before, during, and after it. That matters for 2026. A person might hear that solar maximum has passed and assume the danger is over. It is not that simple. The declining phase of a solar cycle can still produce major storms. Large active regions can emerge. Long-lived regions can return. Coronal holes can send high-speed solar wind streams. Space weather remains active because the Sun does not follow human expectations about neat beginnings and endings. Sunspots are also not randomly sprinkled decorations. They emerge where magnetic flux rises through the surface. Over a cycle, their average latitude changes. Early in a cycle, sunspots tend to appear at higher solar latitudes. As the cycle progresses, they appear closer to the equator. When plotted over time, this migration produces the famous butterfly diagram, a pattern that looks like wings closing inward toward the solar equator. It is one of the most elegant ways to see the Sun's magnetic cycle written across decades. Behind that pattern is the solar dynamo. The Sun rotates differentially. Plasma moves through convection. Magnetic fields are stretched and wound by motion. Poloidal fields become toroidal fields. Toroidal fields rise and create sunspots. The exact details are complex, but the broad idea is that the Sun generates its own magnetism through the motion of electrically conducting plasma. The Sun is not merely hot, it is electromagnetic. When we say the Sun is a magnetic machine, we do not mean metaphor only. We mean that magnetism organizes the visible behavior of the star. Sunspots, prominences, flares, coronal loops, CMEs, the solar wind, and the heliosphere are all tied to magnetic fields. The heliosphere itself is the vast bubble carved by the solar wind around the solar system, extending far beyond the planets. Earth does not orbit in empty space. It orbits inside the extended atmosphere of the Sun. That phrase should feel strange. Earth is inside the Sun's atmosphere, in a loose and extended sense. Not inside the bright body, of course, but inside the Sun's outflowing plasma and magnetic influence. The solar wind streams past us all the time. It is made mostly of protons and electrons, with embedded magnetic fields carried outward from the Sun. Most days it is background. Some days it is disturbed. On rare days, it becomes a storm. Earth's magnetic field meets this solar wind and forms the magnetosphere. On the Sun-facing side, the magnetosphere is compressed. On the night side, it stretches into a long magnetotail. The shape is not a perfect bubble. It is more like a windsock in a river of charged particles. The solar wind presses. Earth's field pushes back. Boundaries form. Particles are guided, trapped, accelerated, and sometimes dumped into the upper atmosphere near the poles. Without the magnetosphere, Earth would be much more exposed. Without the atmosphere, the surface would be exposed in another way, We live under layered shields. The sun throws radiation and particles outward. Earth absorbs, deflects, and transforms them. The same process that protects us also creates the aurora. The shield glows where it is being struck. This is why auroras are so emotionally strange. They are beautiful because the planet is defending itself. Oxygen atoms high in the atmosphere emit green and red light. Nitrogen can contribute purple, blue, and pink. Curtains ripple because charged particles follow magnetic field lines, and because the magnetosphere is dynamic. The aurora is not painted on the sky. It is the sky itself reacting to energy from the sun. During strong storms, auroras move equatorward. People far from the polar regions look up and see a sky they were not supposed to see. That is thrilling, and it is also a sign that the magnetosphere is disturbed on a planetary scale. The same storm that gives someone a once-in-a-lifetime photograph may also force satellite operators to change modes, airlines to reroute polar flights, radio operators to adapt, and grid managers to monitor induced currents. There is a danger in turning every aurora forecast into a threat. Most auroral displays are harmless to people on the ground. You do not need to fear green light in the sky. The atmosphere is doing its work. But there is also a danger in treating aurora as only a pretty tourist event. It is the visible signature of energy transfer between the sun and Earth. It is evidence that our planet is plugged into a larger electrical environment. The current active region story sits inside that larger truth. Reports of X-class and M-class activity from a region still partly hidden or just rotating into view are not, by themselves, a forecast of disaster. They are a reminder that the sun can generate serious eruptions from places we cannot fully see yet. They also remind us that the Earth-facing side of the sun changes day by day. A region that was harmless yesterday because it was aimed away can become relevant tomorrow, as rotation carries it into view. When solar observers say they are watching, they mean something precise. They watch for growth. They watch for magnetic complexity. They watch for delta configurations, where opposite magnetic polarities exist within a shared penumbra. They watch for sheared neutral lines, where magnetic fields on either side of a boundary are stretched past each other. They watch for filament eruptions. They watch for flare frequency. They watch coronagraph imagery after eruptions. They watch solar wind data upstream of Earth. They also watch because the sun can surprise them. A region that looks dangerous can remain quiet. A region that looks modest can produce a well-timed eruption. Forecasting solar flares is partly a matter of probability. Forecasters may assign chances for C, M, or X-class flares over coming days, based on region complexity and past behavior. That is different from predicting a specific flare at a specific hour. The sun is deterministic in a physical sense, but our knowledge of its initial conditions is limited. This should feel familiar. Weather on Earth is also deterministic in principle and uncertain in practice. A thunderstorm forms because physics says it must, given temperature, moisture, instability, and motion, yet local details are hard. The atmosphere is chaotic. The sun's atmosphere is also turbulent, magnetic, and nonlinear. Small changes can matter. Energy can accumulate silently and then release suddenly. The word nonlinear deserves a plain meaning. It means the output is not proportional to the input. A small change can lead to a large effect. A system can sit near a threshold and appear stable, then cross it quickly. A magnetic active region may build stress for days. Then reconnection begins, and the structure reorganizes in minutes. The sun is full of thresholds we can observe but not always predict cleanly. For a listener far from observatories and satellites, the practical question is simple. What happens if a strong solar storm is aimed at Earth? The answer unfolds in layers. First, radiation from a flare reaches Earth at light speed and can cause radio blackouts on the sunlit side. Then, if energetic particles are accelerated into interplanetary space and guided toward Earth, radiation levels can rise, which matters especially for spacecraft and polar aviation. Later, if a CME arrives, geomagnetic storms can begin. A geomagnetic storm is not a storm in the lower atmosphere. It will not blow down trees. It is a disturbance in Earth's magnetosphere caused by solar wind conditions. The KP index is one way to describe global geomagnetic activity. NOAA's G scale runs from G1 minor to G5 extreme. G1 storms are common. G5 storms are rare. Each level is associated with possible effects, from weak grid fluctuations and minor satellite impacts at low levels, to more serious grid, navigation, radio, and aurora effects at high levels. NOAA also uses R scales for radio blackouts and S scales for solar radiation storms. These are not theatrical labels. They exist because different solar phenomena affect different systems. A flare can produce an R event. Energetic particles can produce an S event. A CME can produce a G event. A single active region can be involved in all three, but the impacts are distinct. This is part of why public conversation often becomes confused. People hear solar storm and imagine one thing. Space weather is several things braided together. The first modern space age saw this quickly. Satellites taught us that Earth's environment is not isolated. The Van Allen radiation belts were discovered early in the space program. Solar storms became operational concerns for communication satellites, military systems, navigation, and crewed missions. Each decade added dependency. Each dependency made the sun more relevant to daily life, even as the sun itself remained psychologically distant. It is possible to live an entire life under a star and rarely think about it as a star. We see sunlight filtered by air clouds, glass, trees, and routine. We forget that the source is a sphere of plasma about 109 Earth diameters wide, converting mass into energy in its core, wrapped in magnetic fields that can fling material across the solar system. We domesticate it in language. Sunrise, sunset, good weather, blue sky, then a sunspot appears, and the domestication fails. There is a particular unease in the phrase earth-facing. It makes the sun feel directional. Most of the time we imagine the sun simply shining in all directions, which it does. But eruptions have structure. A CME can be launched more toward one part of space than another. A flare occurs in an active region with a position on the solar disk. When that region crosses the central meridian from our point of view, eruptions from it are more likely to have Earth-directed components. The geometry becomes personal. If an active region is near the eastern limb, it is rotating into view. Eruptions may still be angled away, though not always. Near the center of the disk, Earth is more directly in line. Near the western limb, flares may be magnetically well connected to Earth for energetic particles because of the spiral shape of the interplanetary magnetic field. Each position carries different kinds of concern. The sun is a sphere, Earth is moving, the solar wind spirals, and space weather follows geometry that is not intuitive from the ground. The Parker spiral is one of those hidden shapes. Because the sun rotates while the solar wind flows outward, the magnetic field carried by the solar wind forms a spiral pattern through the solar system. It is a little like water from a rotating sprinkler, though the physics is not identical. This means Earth may be magnetically connected to regions west of the central meridian more efficiently than a simple straight-line picture would suggest. Space weather is not just what points directly at us. It is what connects to us. CMEs also interact with what came before them. A previous eruption can clear material out of the way, allowing a later CME to travel faster. CMEs can merge. High-speed streams from coronal holes can compress slower solar wind ahead of them. The space between the sun and Earth is not empty waiting room. It is a moving medium. Every eruption travels through conditions shaped by earlier solar activity. This is another reason the sun is hard to forecast. It is not only the eruption, it is the environment between the eruption and us. A CME launched into dense, slow solar wind may evolve differently from one launched into a path cleared by earlier activity. Its shock may accelerate particles differently. Its arrival time may change. Its magnetic field may rotate. By the time it reaches Earth, it may not be the same structure it appeared to be near the sun. The best forecasts combine many instruments. Solar Dynamics Observatory watches the sun in multiple wavelengths. SOHO and other coronagraphs watch the corona. GOES satellites measure X-ray flux and energetic particles. DSCOVR and ACE monitor solar wind upstream of Earth. Ground magnetometers track geomagnetic response. Radio observatories listen for bursts. Each instrument sees one layer of the system. Space weather forecasting is the art of combining those layers into a useful warning. That warning must be useful to people who do not think like solar physicists. Grid operators need to know whether to adjust load, monitor reactive power, or protect transformers. Satellite operators need to know whether to place spacecraft in safe modes or expect increased drag. Airlines need to know whether polar communication and radiation levels are a concern. Radio users need to know whether high-frequency paths may fail. Aurora watchers want to know whether to drive north or perhaps south under dark skies. This produces a strange social moment whenever a major active region appears. The same event is watched by scientists, amateur astronomers, satellite companies, power utilities, pilots, emergency planners, photographers, and people who simply want to see the sky turn green. One sunspot becomes many stories at once. For some, it is data. For some, risk. For some, beauty. For some, a reminder that the technological world is less separate from nature than it pretends. The phrase natural disaster usually makes us think of Earth, earthquakes, hurricanes, volcanic eruptions, floods. But a severe solar storm is also natural. It just begins 93 million miles away. It does not care about borders. It does not arrive through the sea or the air in the usual way. It arrives through fields, particles, currents, and radiation. It is a disaster mode for an electrical civilization. At the same time, the sun is not hostile. It is not aiming. It is not angry. It is doing what stars do. The danger comes from our position and our dependencies. We orbit close enough to be warmed and lit. We built systems sensitive enough to be disturbed. We launched machines into space. We stretched conductors across continents. We synchronized markets and networks to satellite timing. We made ourselves powerful, and therefore we made ourselves sensitive. This is one of the recurring patterns of science. A force that seems remote becomes intimate once our technology grows delicate enough to notice it. Before radio, ionospheric disturbances mattered less to daily life. Before satellites, orbital drag from geomagnetic storms was not an operational concern. Before long-distance power grids, geomagnetically induced currents were not a grid planning problem. The sun did not change. We did. The 1989 Quebec blackout is often discussed in this context. In March of that year, a geomagnetic storm caused currents that contributed to the collapse of Hydro-Quebec's power grid, leaving millions without electricity for hours. It was not Carrington scale. It was not civilization ending. It was a demonstration. The sun could couple into a modern grid strongly enough to make a large region go dark. Since then, grid awareness and mitigation have improved, but the underlying physics remains. There was also the July 2012 solar superstorm, a powerful CME that crossed Earth's orbit but missed the planet because Earth was elsewhere in its path. Spacecraft observed it. Had it struck Earth, studies suggest it could have produced severe geomagnetic effects. It became a near-miss story, the kind of event that is easy to ignore because nothing happened here. But near misses are scientifically valuable. They show what the sun can do without requiring us to pay the full price. The May 2024 geomagnetic storm offered another reminder. It produced widespread auroras at unusually low latitudes and created operational concerns for satellites and other systems. Many people remember it through photographs, pink and green skies over places that rarely see them. Space weather professionals remember it as a major storm that tested systems and forecasts. Both memories are true. The same night can be beautiful and operationally serious. The next major active region does not need to be historically extreme to matter. Moderate storms matter because our systems are continuous. A satellite constellation can absorb small anomalies until many occur at once. A radio network can route around disruptions until the disruption covers the region it needs. A grid can manage induced currents until conditions align poorly. Risk often lives not in a single spectacular failure but in the accumulation of stress across connected systems. That is why calm language is important. Panic is a bad way to think about the sun, so is dismissal. The correct posture is attention. The sun deserves the same kind of attention given to oceans, volcanoes, and atmosphere. It is part of Earth's environment, not distant background. Environment. A space weather forecast is not science fiction. It is weather from the star we orbit. For the individual person, the immediate danger from a typical solar flare or geomagnetic storm is usually low. You do not need to hide indoors because of an aurora alert. The atmosphere protects you. The concern is mostly technological and operational. But technological risk becomes human risk when systems fail. Electricity supports hospitals, water treatment, fuel distribution, communication, heating, cooling, food logistics, and emergency response. The sun touches people through infrastructure. This is why the idea of a sunspot as a wound is emotionally powerful but physically incomplete. A wound suggests injury. The sun is not injured. The dark region is a symptom of magnetism. It is a visible place where invisible force becomes strong enough to change the surface brightness of a star. That is more unsettling. The dark spot is not damage. It is power being stored. Power stored in magnetic fields is not obvious to our senses. You can stand next to a magnet and feel nothing unless metal moves. You can walk under power lines and see only towers. Much of modern danger is invisible until it couples into something visible. The sun's magnetic fields are like that. For days they may sit as patterns in data and dark shapes on the solar surface. Then suddenly, they release radiation and plasma into space. There is also a humility in remembering that our best instruments are still partial. We see the sun in wavelengths no human eye can detect. We model fields we cannot touch. We place spacecraft at gravitational balance points to taste the solar wind before it arrives. We convert particles and photons into graphs. We do all of this well enough to protect systems better than before. Yet the star remains capable of surprise. That should not discourage us. It should make the science feel alive. Solar physics is not finished. Researchers still study how flares begin, how particles are accelerated, how CMEs are launched, how the corona is heated, how magnetic fields evolve, and how to predict geo-effectiveness earlier and more accurately. Every active region is not only a potential hazard, it is also a laboratory the size of worlds. A large sunspot region rotating toward Earth is therefore a news story, a forecast problem, an engineering concern, and a philosophical object. It forces us to notice that our planet is not sealed off. Earth is immersed in a solar system that is electrically and magnetically active. The boundary between Earth and space is not a wall. It is a negotiation constantly renewed between the solar wind and the magnetosphere. Civilization lives inside that negotiation. We sleep under it. We work under it. We send messages through it. We navigate by signals crossing it. We place humans above most of the atmosphere, and machines above nearly all of it. We rarely think about the negotiation because most days it holds. The shield holds. The grids hold. The satellites hold. The radio paths hold. The star behaves within tolerances we have learned to survive. But the tolerances are not laws. They are conditions. The sun does not know the acceptable operating range of a transformer. It does not know the radiation limits of an astronaut. It does not know that a farmer's tractor uses satellite guidance, or that a financial network depends on precise timing, or that a pilot over polar regions may need high-frequency radio. The sun does not know us at all. This indifference is not cruel. It is cosmic. The sun gives Earth almost all the energy that sustains life at the surface. It drives climate, weather, photosynthesis, and the food chain. It also produces storms that can disturb the systems built by the life it sustains. The same star is provider and hazard. That duality is not a contradiction. It is what it means to live near a star. The more carefully you look, the less stable the ordinary picture becomes. Daylight is not simple. It is radiation from a nuclear furnace filtered by space and air. A quiet sky is not empty. It is the underside of a magnetic shield. A compass needle is not a quaint tool. It is a small response to a planetary field generated by motion in Earth's liquid outer core. An aurora is not only beauty. It is a visible current system in the upper atmosphere. A sunspot is not a stain. It is a magnetic knot on a star. If the active region now turning toward Earth produces nothing major, the lesson remains. The sun will rotate again. Other regions will emerge. Some will decay quietly. Some will flare. Some will launch CMEs into empty space. Some will aim at planets. Over geological time, stars do not need to be dramatic every day to matter. They only need rare extremes, and a civilization delicate enough to remember them poorly. That may be the most unsettling part. Human memory is short compared with solar time. The Carrington event is less than 2 centuries old, but it belongs to another technological world. The strongest storms in the instrumental record are few. The The worst possibilities are inferred through physics, history, tree rings, ice cores, and near misses. We are building a more electrically dependent civilization during a period when the sample size of extreme space weather is still small. There have been ancient events preserved indirectly, including spikes in cosmogenic isotopes that suggest extreme solar particle events in the past. These are sometimes called Miyake events, after the researcher whose work helped identify one in tree rings. They remind us that the Sun has produced particle events larger than anything measured directly in the space age. The modern technological era is young. The Sun is not. This does not mean we live in constant danger. It means our confidence should be measured. We know much more than Carrington knew. We monitor the Sun continuously. We have warning systems, models, satellites, and operators trained to respond. Engineers can harden systems. Grid managers can prepare. Spacecraft can be designed with radiation tolerance. Astronauts can shelter. Awareness changes risk. Ignorance is more dangerous than the Sun alone. The act of watching is itself a form of civilization. A species that watches its star is a species beginning to understand its place, not as the center of events, but as a participant in a larger physical system. We are small, but not helpless. We are vulnerable, but not blind. We can look at a dark region on the Sun and know that it is magnetic complexity. We can see an eruption and estimate its arrival. We can warn each other before the sky glows. Still, there is something eerie about the delay. A flare reaches us in 8 minutes. A CME takes longer. The light announces what has already happened. The plasma arrives later, carrying the deeper consequence. We live between signals. First the flash, then the waiting. Instruments update. Models run. Forecasts shift. The cloud crosses millions of miles of space. Somewhere upstream of Earth, a spacecraft samples the magnetic field, and only then do we learn whether the storm's orientation is the kind Earth can shrug off or the kind that opens the door. That waiting is part of the drama of space weather. It is not cinematic in the usual way. No wall of fire appears in the sky. No countdown is visible to the eye. Instead, there are numbers changing on screens. Solar wind speed, density, temperature, magnetic field strength, BZ, KP, proton flux, X-ray class. It is a quiet suspense, the kind suitable for a civilization whose greatest vulnerabilities are hidden in systems most people never see. The phrase BZ may sound small, but it carries weight. It refers to the north-south component of the interplanetary magnetic field. When BZ is strongly southward for a sustained period, geomagnetic activity can intensify because energy couples more efficiently into Earth's magnetosphere. A CME with a strong southward field is more concerning than one with a northward field, even if both arrive with similar speeds. Direction inside the magnetic cloud can decide how deeply the storm connects. This is difficult to communicate publicly, because people want simple answers. Will there be aurora tonight? Will the grid be safe? Will satellites fail? Science often answers with probability and conditions. If the CME arrives earlier, if the magnetic field turns south, if density remains high, if the cloud's core strikes Earth. These ifs are not evasions. They are the actual structure of the problem. A mature relationship with the Sun requires comfort with conditional thinking. A strong flare is not the same as a strong geomagnetic storm. A big sunspot is not the same as an Earth impact. An aurora forecast is not a guarantee. A low probability is not zero. A scary headline is not a forecast. A calm forecast is not permission to stop watching. The Sun lives in probabilities until an eruption arrives. This is why the best version of the story is not that a monster sunspot is coming to destroy us. That would be easy and false. The better story is that a powerful magnetic region is rotating into view, and it reveals how exposed our modern world is to processes most people never learn to name. It gives us a doorway into the physics of a star and the fragility of an electrical civilization. Consider the phone beside you, or the router in another room, or the GPS signal that tells a delivery vehicle where to turn. None of these objects look solar. They look human. Plastic, glass, metal, code. Yet they depend on a space environment kept within usable limits. They depend on satellites not being too disturbed, signals not being too distorted, grids not being too stressed. They depend on the Sun remaining, in a practical sense, polite. The Sun is not always polite. It releases flares without warning to us. It throws CMEs into the dark. It sends high-speed streams from coronal holes. It bathes the solar system in ultraviolet light and charged particles. It shapes planetary atmospheres over time. Mars may have lost much of its atmosphere partly because it lacked the same kind of global magnetic protection Earth has. Venus, Earth, Mars, and the Moon each tell different stories about what it means to exist under solar influence. Earth's story is the fortunate one, but not the invulnerable one. Our magnetosphere protects life at the surface. Our atmosphere absorbs harmful radiation. Our planet's interior generates the field through the motion of molten iron alloy in the outer core. Deep beneath our feet, convection and rotation help maintain the geodynamo. Above our heads, that field stretches into space and meets the solar wind. Protection begins underground and reaches beyond the atmosphere. There is poetry in that. The shield against the sun is born inside Earth. The core moves, the field rises, the solar wind presses, the aurora glows, the ground and the sky are connected by magnetism. A storm from the sun can induce currents in rocks, wires, and transformers because the planet is not electrically isolated. The Earth is a conductor inside a changing magnetic environment. If you have ever held a magnet near a coil and watched a current appear, you have seen the seed of the problem. Changing magnetic fields induce electric currents. A geomagnetic storm changes the magnetic field environment over large regions. Long conductors give induced currents a path. The physics is not exotic. It is the same electromagnetic law taught in classrooms, scaled up until continents become part of the circuit. Scale is what turns familiar physics into cosmic unease. A magnet and coil on a desk is a demonstration. A CME striking Earth is the demonstration enlarged until the laboratory is the planet. A solar flare is not magic. It is electromagnetic energy from reconnection. A radio blackout is not mystery. It is ionization changing how radio waves propagate. An aurora is not supernatural. It is atomic emission. The facts make it more astonishing, not less. The old myths were wrong in mechanism but not in emotional response. People saw lights in the sky and understood that something beyond ordinary life had entered the night. They lacked plasma physics. They did not lack awe. Modern science replaces the omen with explanation, but it does not remove the strangeness. It sharpens it. Now we know the lights are particles from a star guided by a planetary magnetic field into an atmosphere thin enough to glow. The active region turning toward Earth may give us only a mild show. It may give us nothing. It may produce flares that affect radio and then fade from public attention. It may launch a CME that produces auroras for northern observers, or it may become one more watched region in a long record of solar behavior, useful to forecasters and researchers but not dramatic for daily life. The uncertainty is honest, but even a quiet outcome leaves behind a useful thought. The sun is never merely rising, it is rotating, it is churning, it is twisting magnetic fields beneath and above its visible surface. Somewhere on the disk, spots grow. Somewhere at the limb, prominences lift. Somewhere in the corona, loops brighten. Somewhere in the solar wind, disturbances move outward. The star is active whether we are paying attention or not, and we are increasingly forced to pay attention. Human life is becoming more orbital, more networked, more electrical, more dependent on timing. We are not retreating from space weather. We are moving deeper into its reach. More satellites, more lunar missions, more crewed exploration, more autonomous systems, more precision navigation, more reliance on uninterrupted power. The future is not less vulnerable to the sun, it is more aware of the need to live with it intelligently. There is a quiet irony here. We often imagine advanced civilization as escape from nature. Cities replace forests. Satellites replace landmarks. Digital networks replace physical distance, but the more advanced the civilization becomes, the more deeply it depends on invisible natural systems, space weather, orbital debris, atmospheric drag, geomagnetism, solar cycles. Progress does not remove nature, it reveals new layers of dependence. The sun, then, is not only a star in the sky, it is part of the operating environment of Earth. It is a variable input into the systems that make modern life feel stable. When a huge active region rotates toward us, it is a reminder that stability is managed, not guaranteed. Our calm days are produced by shields, forecasts, engineering, luck, and the fact that most solar eruptions do not line up perfectly with us. Maybe that is why sunspots feel so compelling. They are visible warnings on something too bright to look at directly, dark marks on the source of daylight, places where the sun's hidden magnetism writes itself in contrast. They invite the old human instinct to read the sky for meaning. Science tells us what the marks are. It does not tell us to stop looking. Tonight's story began with something turning toward Earth. But the deeper story is that Earth is always facing the sun, and the sun is always doing more than shining. We live in the light of a magnetic star. We live under a shield we cannot see. We live inside a technological world that works because fields remain calm enough, signals remain clear enough, and the great storm machine at the center of the solar system spends most days looking quiet from 93 million miles away. The open question is not whether the sun will erupt again. It will. The question is when the next truly consequential eruption will happen, where Earth will be when it does, and whether the systems we have built will be ready for a star that does not know it has become part of our infrastructure. Perhaps the most honest way to think about the sun is not as friend or enemy, but as scale. It is the scale of our dependence, the scale of our ignorance, the scale of our progress. A dark spot on its surface can be larger than Earth. A magnetic cloud from it can surround our planet. A glow in our sky can reveal a storm in space. The ordinary day is not ordinary because the universe is calm. It is ordinary because, for now, the violence is being held at a distance. Subscribe to Dark Matter Radio if you want more long-form journeys into the science that sits just behind ordinary reality, and leave a comment with the question this leaves you with. Is our civilization prepared for the sun as it really is, or have we only learned to live with the quiet version of it? Until next time, keep listening to the dark. There is another quiet layer to this story, and it sits in the difference between seeing and understanding. Human beings can see sunspots only with proper protection, and most of us never do. We see the sun as a featureless disk because our eyes cannot safely examine it. Instruments change that. They turn a dangerous brightness into information. They reveal granulation, magnetism, ultraviolet structures, X-ray loops, and eruptions that would otherwise remain hidden inside glare. That transformation from glare into information is one of the great achievements of solar science. The sun is the nearest star, but nearness does not make it easy. It is too bright, too hot, too dynamic, and too complex for casual observation. Every clean image of its surface is the result of careful filtering. Every forecast is the result of a chain of measurements. The familiar star has to be translated before it can be understood. Even the phrase solar surface can mislead. There is no hard ground there, no crust, no place where a probe could land. The photosphere is a visible layer in a continuous body of gas and plasma. Above it, the chromosphere flashes in red hydrogen light during eclipses. Above that, the corona stretches outward, faint and hot, normally hidden by the sun's brightness. During a total solar eclipse, the corona appears like a ghostly crown, reminding anyone watching that the sun has an atmosphere larger than the thing we call its edge. That crown is where many space weather stories begin. Magnetic loops rise there, prominences hang there, CMEs erupt through it. The corona is thin, but it is not empty. It is structured by magnetism, heated by processes we are still trying to fully understand, and connected to the solar wind that fills interplanetary space. When the corona changes violently, Earth may eventually feel the result. The more one studies this system, the more the distance between the everyday and the cosmic collapses. A transformer hums on a street corner. A satellite sends a timing signal. A pilot crosses a polar route. A child sees aurora photographs online. Each of these things can be connected through enough physics to magnetic reconnection above a sunspot. The chain is long, but it is real. A large solar storm also exposes a problem of imagination. We are used to local hazards. A river floods one valley. A cyclone strikes one coast. A wildfire follows a landscape. Space weather is different because the same disturbance can affect an entire hemisphere of radio communication, a constellation of satellites and electrical systems across regions at once. It is not everywhere in the same way, but it is not local in the ordinary sense either. That wide reach is why preparation is shared across disciplines. Solar physicists study the eruption. Spacecraft engineers study charging and radiation. Atmospheric scientists study the ionosphere. Grid engineers study induced currents. Emergency planners study consequence. No single field owns the whole problem. The sun forces collaboration because its effects move from plasma physics into economics, transportation, communication, and public safety. There is also a psychological challenge. Space weather often becomes visible to the public only when it becomes beautiful. The aurora is the publicity department of the magnetosphere. It photographs well. It spreads across social media. It makes people look up. But the less photogenic parts matter just as much. A transformer warming under induced current does not look cosmic. A satellite timing error does not look like a storm. A radio blackout may be experienced only as silence. Silence is an underrated consequence. When high-frequency radio fails, the failure is not dramatic to someone outside the system. But for aviation, maritime communication, emergency networks, and remote operations, silence can be serious. The sun can make the upper atmosphere less cooperative. It can turn a normally useful layer of charged particles into a shifting mirror that absorbs, bends, or scatters signals unpredictably. None of this makes the sky less beautiful. It makes beauty less innocent. The green curtain is oxygen speaking after being struck. The red glow is another altitude, another transition, another kind of atmospheric response. Every color has a cause. Every ripple has a field behind it. To watch an aurora with that knowledge is to watch Earth and the sun communicating in a language older than life. That language will continue after this active region is gone. The sun will rotate. The spot will decay or cross out of view. New regions will emerge. Forecast pages will update. Most people will return to not thinking about the star above them, yet the infrastructure will still be listening. Detectors will still be counting particles. Magnetometers will still be tracing disturbances. Somewhere, someone will still be watching the solar limb for the next dark shape to appear. The quiet work matters because the moment of need is often brief. A warning issued hours before impact can let systems prepare. A forecast of radio blackout can change operations. A radiation alert can alter decisions in space. The difference between surprise and preparation may be a graph, a satellite, a model, and the willingness to take an invisible hazard seriously before it becomes visible.